Good morning. Welcome to knowledge-based recommendation. So we've talked about content, we've talked about collaborative filtering. Now we need to understand how we can build systems that have expertise, and why would we want to do that? So here the requirements may be very, very specific and may be very difficult to extract based upon some kind of understanding of the domain. We live in a data science oriented world where we believe we have lots of data, but that may not be the case. But here we may actually want to take part of the definition of the user, which is stored in a rule-based manner, rather than what we've looked at so far, where the user has been represented as some kind of point in a space, and we've been able to compute similarity using cosine or something similar. What we're going to do in this particular class is to talk about knowledge models. Those knowledge models may be based upon product, but they may also be based upon user preference. So even though this slide shows knowledge models at the bottom, really they can actually encapsulate aspects of user behavior as well. And what we're doing is basically gluing together a view of the user, a view of the product, knowledge models, putting everything into our black box to come up with a recommender system, much as we've been trying to do over the last few classes. So why do we need this? Well, it's very often the case that products don't have a very large number of data points that allow us to create statistically relevant or applicable models. If we look at the right-hand image there, the Bugatti Chiron, or whatever it is a very rare commodity. There are going to be very few people who are going to desire this product, in no small measure because it's a very expensive product. The same thing is true of this luxury house, which would have characteristics which only the very wealthy might actually be able to afford. Characterizing such things, because of the number, very, very low. Similarly, we may have things that require temporal information to be included, and the rules, the models that we're using, may require constant refinement, or we may need to decide upon the applicability of a particular model using some kind of rule before we then use some kind of statistical model. The lifestyle choice is something that is applicable here. The final bullet point is probably the most significant. I may actually want to put constraints on the recommendation. I might want to say that, the color of the car should be black, or as will be appropriate for this particular class set of slides, it'll be related to cameras. And I should point out at this point that there's a certain amount of software that goes with this particular lecture that I built, which is a RESTful configuration engine for cameras. That the software for that can be found in sub-bullet 12. The sub-bullet 8 allows you to explore configuration of a product with the underlying product database that's displayed in these particular slides in a moment. The list of products which are shown on slides, that can be accessed directly by looking at sub-bullet 9, and the code for the engine which drives the configuration process can be found by accessing sub-bullet 10. So lots of things to access if you're interested. So knowledge-based recommendation systems have a number of characteristics to them, and we can incorporate constraints, so things that certain variables are linked. So we can have something that must be less than a particular value, more than a particular value, within a set of values, within an interval. And this needs to be provided both at the product side of things and also on the user side of things. And there can be models underlying the relationships between variables as well. So these constraints need to be explicitly represented and manipulated during the product satisfaction process. Then there's case-based, where a user might want to define something in one domain, for example, fit for purpose, and that be translated to one of a set of cases of parameters that are associated with the products themselves. So, you know, if a user is interested in a camera for a particular type of photography, then that would translate possibly to its lens requirements and so on. If I am interested in buying a particular car for a particular purpose, that purpose itself would once again translate to parameters that would be defined on the car itself. For example, if it's for a family, space, carrying capacity might be an issue, and that would be translated to the number of seats that it has, the safety record of the car, and so on. What is somewhat unique with respect to knowledge-based recommendation system is that users specify requirements, then the system tries to satisfy those requirements, and in the case where no solution will be found, the system will actually make recommendations on things that are close to but do not satisfy the original requirements. So they will endeavor to relax these requirements that a user has, and possibly do that in a semi-automated way or through a conversational interaction with the user. The knowledge base then is this thing that separates the user model from the items that have their own domain properties. And then the knowledge base will also deal with variables that store things that the user wants and things that the items themselves have characteristics for. Again, in the case of a camera, we would have features that would be related to the magnification, whether they're waterproof, and so on. Then the knowledge base would also have a set of constraints, rules, logical implications. If a user requires something, then the item itself should possess a feature that is related to the requirement. It may not be that the user specifies the requirement in the domain of features of the products. Again, going back to the statements earlier about cameras, a user might want a camera that is to be used for sports photography. So then the requirement for a very long-range zoom may be an implication of that particular requirement. The feature, long-range zoom, would be part of the product's specification, so there needs to be a mapping from the user requirement to the feature or features that the item possesses. We then need to decide whether the user absolutely has to have that feature or that requirement, or whether it's something that's a nice to have. And then we talk about whether this is a hard requirement or a soft requirement. And we can also talk about whether a requirement is more important than another requirement. So the constraints, these requirements, can be weighted, and those would be part of the preferences, the model, the user profile that you would either specify directly or possibly compute based upon some kind of clustering process. So these constraint-based recommender systems have the functional requirements for fulfilling an applicable set of constraints, deciding on whether they can actually be satisfied, whether I can relax certain of them, and then ideally the system itself would be able to explain how it came up with its conclusions. So it would provide some kind of textual response that would explain which rules were being applied and how they were being applied. We won't really touch on explanations in this particular class. There is a whole chapter in the book on explanations which won't be covered, but it is there should you choose to consume it. So the tasks, what do I have to do? So I have to find a set of user requirements, a subset possibly, such that the one or more items fulfills everything. So ideally I might want to ask the user which can be satisfied, or they specify that at the outset. Ideally, at first blush, we will try not to violate any constraints, but in the case of an infeasible solution, i.e. a null set of products being returned, then I need to decide what I should relax first. If I do have to relax constraints, then I want to satisfy the maximum set of weighted constraints. So in the case of all, I'm golden, whereas in many cases I have to decide in what order I will relax constraints. So some constraints are more important than others, and those hopefully would be implied by the user requirements or their user profile, in fact. In this class, with the engine that I'm going to show you, you are basically offered the possibility of a constraint being optional or must be satisfied. There are no two ways in between. But we could easily extend the model so that constraints were satisfied in a particular order or relaxed in a particular order. That would just be an extension of the basic model. And once we have the ability to relax in a particular order, then assuming weights associated with constraints, it becomes a matter of sorting based upon those weights to give us ordering. So we'll assume that that kind of functionality could be added to the model that we will obtain by the end of this particular slide pack. So once we end up with a set of satisfiable constraints, then the user will have presumably a model of desirability, you know, whether cost is the most important or whether quality is an important thing. We have things which are more important than other things when we are doing our evaluation. That's how we end up with making a purchasing decision at the end of the day. So based upon that model, we will then ultimately rank the products which are returned to us using the the user profile model that we have either set up by the user initially or inferred by computing some kind of like. This user is like some other. So here's an example product catalog, and this is the catalog which is explicitly stored in the model that I've created for you. So you can see that there it is at the bottom. Here's the product configuration model that I have. When you're reviewing this particular video, you'll see that there are 8 products. Each particular product has a number of features. Here they all happen to be the same, but it isn't necessary that they need to be. You can have a heterogeneous catalog and work with a heterogeneous catalog. You can see that that catalog is explicitly shown at the bottom of this particular piece of prologue, and it's available to you inside of the model. We'll talk some more about that shortly. The textual description of those 8 products, you can see here in this table. They have 7 attributes: price, the number of megapixels the camera supports, whether you have an optical zoom, whether or not there's an LCD screen, whether or not the camera can do movies or not, whether or not it supports, has a microphone and therefore supports sound, and whether or not it's waterproof. So the kind of requirement that a user can specify, we see at the bottom of the slide, the price should be lower than 300 euros. And you can see that if we were to satisfy that, all products 1 through 8 would actually be satisfied. The camera should be suited for sports photography. Now that's very different because the requirement is not specified in the domain of the features that are defined for the camera itself. So we need a model which can translate the requirement for sports photography to a set of features that are available for cameras in the product catalog. So that's where the requirement there comes from. So what we have set up for ourselves as a recommendation task is a constraint satisfaction problem, where what we are doing is taking variables that define products and variables which define users in some domain. So we've got variable values that exist for a particular domain, so we can choose from those values. That's all we're saying. We have a knowledge base which creates or stores all of the relationships between entities within the domain. For example, if the purpose is a travel camera, then the focal length should be less than 28 millimeters. So we do a translation between one domain and another. On the previous slide, we were doing a translation between purpose, and we were we would infer the values, the ranges that would be applicable for the features within the photography domain. So we have this specific requirements for the user. So what they want, here's an example on travel. We've got the product catalog and we've got this knowledge base, which is rules that connect things from different domains. So we are satisfying, given user and product information, the domains, i.e. the values which can be associated with particular variables, and then we are trying, given the requirements of the user, the product catalog, and these rules, to come up with values of the variables for xi and xu. And that's what the second bullet says. It'll either be some set of variables x sub I that are either satisfiable or not, and in the case of unsatisfiability, we want to fix it so that we can come up with a set of variable values that is non-empty. That's our goal. So we've got the SRS, that's a mapping from the user domain to the feature domain. We've got requirements of the user. So for example, there's the mapping of on travel to waterproof and megapixels, and we've got a rule base that does the transformation. We would typically want to provide defaults for the values of features, or we would ask the user directly for a value if we require it during the process of rule evaluation, inferencing, in order to come up with a set of recommendations. We can, inside of our system, incorporate the ability to say, if I don't have a value, will this value actually do? So will the closest value do? I.e., will a value less than this do? Or a value more than this do? Will a value from this set do? If you asked for 8 and I only have 1, 2, 3, 4, and 10, will one of those values do? So we need a mechanism for either asking or relaxing. Relaxing being modification. That's what we're asking for. In many cases, we will do semantic or common sense modification. So if somebody has asked for 6 megapixels, for example, and we can give them 8, then we'll give them 8. We'll assume that that's a good thing. If we've asked for 300 as being the price, obviously anything less than 300 is probably something we should consider for them. So this is a bit different from a constraint solver. We're not just trying to find out whether we can or cannot instantiate the variables. What we're willing to do is actually do some manipulation of the query such that we can ultimately come up with an answer. Think of this, we're building this system to do e-commerce. And so the last thing Amazon wants to do is to tell you that it can't actually satisfy your request. It wants to give you something that is at least in the ballpark, which is why when you ask for a particular product, it will always give you something back. And sometimes you probably wonder, why did it give me that? It wants you to have something to choose. It doesn't want to say, I have nothing. That's the difference. It's because the domain of application here is e-commerce. So what we're trying to do is solve a query given a set of products, P, and a set of criteria that the user has specified, that Here we are just assuming is mapped by some model that's ultimately going to provide us with features in the domain itself. Here I've got a query for the number of megapixels greater or equal to 10 and the price less than 300. And if we look at our database from the previous slide, although I'm going to go on to the next one, we will find that it's P4 and P7. So if you look at the megapixels greater or equal to 10, you can see we've got that satisfied, and the price less than 300. Only the megapixels is actually a constraining factor because all of the cameras in this particular product database are less than 300 euros. So it's only the megapixel constraint that actually is going to limit the response. And so the system itself would hopefully return P4 and P7. Now I invite you to go to the online engine and try out that query, and you should see that you get back P4, P7. The query that could have generated the result that you see on the title of this particular slide could have been asked in the form of the camera should be suited for sports photography. And in that case, the mapping that's built into the model I've provided for you, I believe, is the design for purpose. You can see that for sports, I've said the optical zoom must be greater than 4.9, and it's got to support movies and sound. So my example, and this was line 69 that you see on the screen here, but in the slides that's actually converted to megapixels greater than 10. The purpose here is to show you that there is this intermediate model that is given a design for purpose, then that purpose maps from that purpose to a set of features that can be completely different from one purpose to another. If you look at travel, it's just waterproof. If it's portraits, we want it to have megapixels greater than 9.9. If it's cheap, we want it to be less than 155 euros. They don't all have to have all of the features represented. The purpose predicate just gives me a user view mapped to a feature view. So the user specified his or her preferences all at once, or possibly in some kind of interactive dialogue. The system that I've provided for you doesn't allow for that interactivity, but that could easily be added. The answer being as the system itself would proceed, and if it doesn't find a value, it would ask the user, and then that value would be used during the rest of the inferencing process. Alternatively, as is provided, I've given you a screen that allows you to actually configure all of those features. And you can see that I've got all 7 features from the camera domain explicitly represented, and you can specify whether they are to be optional or whether they are to be equal. And if they're not equal, then there is a semantic constraint applied where in the case of some features they are implied as a greater than constraint, or greater than or equal constraint, or in the case of cost, for example, it's semantically interpreted as a less than or equal to constraint. So that's, you can either be explicitly equal, or you can be implied to be less than or equal in terms of cost, or greater than or equal to in the case of megapixels, optical zoom, or LCD size. That's why the slide is, the dialogue, the wizard, is actually represented in that particular way. So the interaction mode here would be is that the user would provide their constraints, some of which might be optional, and then the system will return some kind of response saying these are the products which meet your requirements, and will actually specify whether or not it had to relax certain criteria in order to come up with that response. You would expect then that the user would modify their requirements, possibly to say, oh, well, that isn't optional, I really want that to be true, and you would go through this refinement process. The wizard that I've provided it doesn't really engage in that kind of dialogue, but I'll talk about dialogue systems towards the end of this slide pack. So by providing defaults, then so that the user doesn't have to provide all pieces of information. So if they provide nothing, we will assume defaults for certain parameters, and you'll get back more. Again, the goal is not to force the user to be knowledgeable to get an answer. We want to get a set of things back quickly from which they can choose, and thereby refine their search. And in order to do that, we want, where possible, to provide values that doesn't return the entire database. Again, the wizard which I've provided doesn't actually provide a lot of defaults, but that could easily be added into the system. And if you're interested, the prologue is provided for you to modify these things. It's not particularly complex prologue with respect to modifying a few facts here or there. I don't suggest you try to modify the constraint solving mechanism, but again, no fair, no foul. If you modify it and it's broken, you just reinitialize from the designer.txt file, which is provided inside of the project, which I've linked on today. So the defaults which may be provided might just be raw numbers. They might be an example from an enumerated type, or it could be a derived default. So that is something where if I've got a particular value like price, then that might imply a different default in terms of the megapixels that I can get from the system, rather than assuming that, well, if a megapixel requirement isn't provided, then I'm just going to give you a set value. If somebody's already specified a price, then that might imply a lower level default. So dependent or derived defaults are different flavors of the same thing. There is some underlying model that connects one feature to another. The important thing is, though, that you want to reduce the cognitive overload on the user. You don't want them to specify parameters for everything. So you want, insofar as is possible, to provide defaults and have the users only say, no, that doesn't meet my needs, and back off from those default values if the user's search is not satisfactory. The really hard thing is where you can't find a solution, and then it becomes a matter of constraint relaxation. And now what we're going to talk about is how we can compute those sets of conflicting constraints, and how we can go about relaxing them. And the idea is we're going to relax constraints until we can come up with a solution. We do not want to return a null set. And then The user potentially is going to modify those repair proposals, i.e. the set of violated constraints, to say, no, this one I'm not willing to allow to be violated, and continue through a dialogue in that manner. So the diagnosis is coming up with the set of requirements which cannot be satisfied. And there could be multiple different sets, because two constraints may actually be things that cannot be satisfied, but if I have another couple of constraints that could be relaxed, then the first set would no longer be a problem. So there are possible competing sets of conflicting constraints that we can come up with. Don't just assume it's one set of constraints. So here's an example, and we're going to show how this can be derived. What we want to do is to come up with a minimal set of requirements that need to be manipulated in order to satisfy a requirement. So here's a query at the top. So I have 4 requirements. Requirement 1 is on price, being less than or equal to 150 euros. Requirement 2 is that I must have a 5x optical zoom or greater. Well, this is actually equal to. Then the requirement 3 is that I must have sound, I must have a microphone, and requirement 4 that the camera must be waterproof. Requirements 1 and 2 are things that I cannot satisfy concurrently. That's a conflict set. So if I relax requirement 1, I end up with still that I have a conflict set that includes requirement 2 and requirement 4. So even though I've relaxed R1, I end up with R2, R4 conflicting. Similarly, if I relax R2, then I end up with R1, R3 being in a conflict set. So if I relax R3, then I end up with a diagnosis that if I am willing to relax R2, R3, I can come up with an answer. If I'm looking at the left-hand side of the tree, I'm sorry, I went not in a breath-first manner, then by relaxing R1, I end up with R2, R4 in a conflict set. And if I relax R2, I can actually come up with an answer. So my diagnosis then becomes, if I relax R1, R2, I can come up with an answer for sound and waterproof. If I relax R4, I can come up with an answer so that R2, R3 can be satisfied. So here there are 3 different diagnoses that if I'm willing to relax R1, R2, R1, or R1, R4, R, or R2, R3, then I can actually come up with answers. So that way of proceeding is actually stored in an algorithm called Quick Explain. And Quick Explain actually takes your set of requirements, takes your set of products, and it actually outputs a minimal conflict set, this thing called CS. And so what I'm going to do is go through an example of this particular algorithm. So it's easier to look at the annotated algorithm with the values of the variables which are instantiated in red on the following slides, rather than just go through this particular algorithm. So quick explain is something that allows you to compute in a mechanical way the conflict sets that, if they are relaxed, allows you to come up with an answer to a particular query that contains a set of feature requirements for that are in your product database. So what is returned from the quick explain algorithm, this QX prime function, is a minimum conflict set. And there are, as we've seen on the previous slide, multiple possibilities for this. And we are just going to compute one of them in the following algorithm, okay? In any execution of QX prime, then if the requirements that have been provided to the function only contain one requirement, then we're done. Because if we relax it, we know that we can satisfy the query because we've got nothing to satisfy. The requirements are going to be an empty set. So we know that there is no reason to try harder to relax more requirements. The quick explain algorithm is a divide and conquer algorithm, because you can see that QX prime here, the function, invokes QX prime on a breakdown of the current set of requirements. If you look at line 4 of QX prime, or line 3 if you don't include the function name, that says let R1 through Rn equal REQ, rec, then what we are doing in this function is actually recursing now with half of the requirements. Rec1, rec2 are a breakdown of that set of requirements which we do a split on. Obviously we can do the split in many different ways. Here it's just shown as being, I'm just going to take the first half and the second half and try and satisfy the requirements where I am assuming that I've relaxed a bunch, and then I'm just going to see what the other, the minimal set of minimum conflict set is on the requirements for the remaining, in this case, rec2, and we just provide the union of the responses of the recursively called QX prime to give us the minimum conflict set of the initial requirements. So the possible set of answers, as I say, there are many possibilities for minimal conflict sets, come from the way in which I decompose REQ to REQ1 and REQ2 inside of QX prime. So this is the example that we're going to go through with quick explain. So the coding of QExplain is shown on the previous slide. It is a recursive invocation of this QX prime algorithm. And so in this particular case, what is going to happen is that QX, which is the original query with the original product database P, which is this set P1 through P8, the requirements R1, R2, R3, R4 is this REQ value, And so we are invoking qx prime with now these two variables, which are initially empty sets, the product database P, and the set of requirements. So we decompose qx prime following down to invocation 3 here. We are saying that we are instantiating those two first arguments to be the first half of the set, R1, R2, and then we are going to see if we can solve the problem for R3, R4. So that because the constraints still cannot be satisfied, that invocation of qx prime itself spawns a new invocation to qx prime, which requires that I end up trying to solve for R1, R2. That when I do the recursive call on R1, R2, that's going to end up being unsatisfiable, and it's going to recurse to provide two recursive calls, each with a single requirement, R1 and R2. That isn't going to require any kind of further recursion because we simply have a single requirement that can be relaxed. So those calls, the recursive calls to qx prime shown as 4, is actually going to be R1, R2. So the minimal conflict set for R1, R2, for R1, R2, R3, R4, from that second invocation of qx prime is going to be R1, R2, which means that I can return from the second call to qx prime that came from 2 with R1, R2. The first call, qx prime that was represented in 3, can't possibly be solved because R1, R2 are already considered to be part of the things that I must satisfy. So the R3, R4, not a problem because I don't need to relax anything else for those. So the extra minimal conflict set for R3, R4 requires nothing. So the union of the empty set and R1, R2 is what is returned from 2, which then is R1, R2. So a minimal conflict set for R1, R2, R3, R4 is simply R1, R2. So let's go to showing all of that in terms of an invocation of qx prime. So that's what we're going to do. So we're going to use qexplain. So here we go. I hope that this is more helpful. And of course, given the slides themselves, you can actually flick backwards and forwards through the invocation to see what these calls are actually doing. The prologue that I provided to you doesn't actually do this work explicitly. It is doing simple breadth first search, which is the search algorithm built into basic Prolog. So here we go, we've got B and sigma both empty, and we are calling the QX prime with the full set of requirements because we cannot satisfy those requirements at all. So this is going to cause us to invoke QX prime with now the products P that were given to us. That's going to be common. So if I cease to refer to P at this point, don't worry about it because P is common. It just gets carried all the way through. That never changes. But what we've done in this invocation is split REQ now into REQ1 and REQ2. REQ1 is R1, R2. So we are going to provide the union of QX prime with the invocation of B with R1. So the new value which is being passed to B is B union REQ1. So that becomes R1, R2. The second value of the third argument is itself R1, R2, and then the remaining arguments is the remainder REQ2, which is now the set R3, R4. So we are now on the next slide performing the recursive call to QX prime as shown on this particular slide. So here we go, we've got R1, R2 and R1, R2 as instantiated for B and sigma, and now we're trying to solve for R3, R4. So what are we going to end up doing? Well, once again, we cannot satisfy the requirement for R. So in this case, we cannot satisfy the requirement B, which is shown in line 2 of the function, where line 1 is the function itself, the formal argument specification for the arguments. So we cannot satisfy that. The requirement now is R, which is, it isn't a single requirement, so we can proceed. The fourth line, we are going to break down REQ now into 2 halves, which means that the REQ1 is going to be R3, REQ is R4. So we need to recurse again, which means that we are going to call QX prime with now B augmented with rec1. It's the union of B and rec1. Sigma now is R3 because we're only looking at the recursive call, not the satisfaction of this call up above. And the single remaining requirement, R4, is the rec2 value. So we're now going to satisfy this QX prime call. So you can see that we are failing on the R1, R2. The call comes back as empty for sigma 2. we're now going to do the recursive call on QX prime with just R1, R2, which itself is now going to end up with a recursive call for R1 being the first half of the breakdown of R1, R2. So we are going to end up with two recursive calls. This is the first recursive call. Well, we can satisfy that because it is a single requirement, so we return it. So that return value is R2. So now we can try and satisfy the second QX prime call, which is going to have the values of R, just the single set R2 for the first two arguments and the requirement R1. Well, we can always satisfy the, in the case of rec, that is just a single requirement, so it's going to succeed here. So the two values for that recursive call are going to be R2 for the first one, R1 for the second one. So the return value for QX prime, this first recursive call, is R1, R2. And that then unravels all the way up to the top. I could have had an extra slide here because that QX prime call here that is being returned, that's returning R1, R2. And the union of an empty set plus R1, R2 is R1, R2. So there is an extra slide, if you will, that would show that. I just have missed it here. Okay, but you can go back and review this set of invocations, and hopefully you can convince yourself that QX prime is actually doing a job of computing the minimal conflict set. But it's just one answer. The solution that's been computed in the previous n slides, where n's about 8, is R1, R2, and so it's the relaxation on price and optical zoom. But if we were to decompose the requirements being passed into the QX prime algorithm in a different way, rather than just splitting in the middle, but actually computing some permutation and then doing a split, we could actually get two other solutions, D2 and D3, which would allow me to say that R1, R4 or R1, R2, R3 are in fact also things that I can work with. The system, the prologue system that I've provided for you, actually returns as part of its calculation the set of optional features that need to be relaxed in order for a solution to be obtained. So if you have specified no optional features, OF will end up being instantiated with the set of features which need to be relaxed in order for an answer to actually be generated. So that's the interpretation here. So repairs then become the adaptation to the original query. So we take the initial requirements, remove the set of requirements which we have computed as diagnoses, minimal conflict sets, and remove them, and then run the query again. And we will find that if we do that with D1, D2, D3, and perform the request again, we will actually get different sets of products returned. And so I leave that as an exercise to you to perform with respect to the prologue. But if we repair for one minimal conflict set, it will obviously provide for a different set of products than if we use a different minimal conflict set, the D1, D2, or D3. So that little system that I provided to you actually has a small number of components to it. This is a simplification of the code itself. The code works by receiving a set of requirements in RF, and it can also receive a set of optional features. So requirements which may or may not be provided by a particular product. And then the P argument is itself a product which either satisfies the requirements or satisfies the requirements less the set of optional features. So think of the optional features as being part of the minimal conflict set. So it does this by looking at each product in turn and finding the product features associated with the product, and then asking that set of product features whether they correspond to the set of requirements. And the has predicate is just a way of iterating through the set of features and saying whether or not the feature is okay. And a feature is either okay if it has the value, or it's possibly a member of the values which can be specified for a particular feature. If the user is asked for a greater than constraint, then is the value greater than the value of the particular feature? Similarly, less than. And then the final version of OK is a bit more complicated in the sense that we can ask whether or not there's the value is of a more complex nature. And you can see that OK itself supports this idea of recursion. So as long as a feature can actually be represented with some kind of named predicate, then we can ask whether or not that value associated with that predicate meets our desires. And so a more complex version of this code is actually in the prologue, which is seen here. I've updated it recently, but you can see it's got a has, and instead of OK, it's called check OK. It's slightly more complicated in the code that I provided, in that there's an extra argument, there's an extra clause called check OK on line 42, but the code is operating conceptually in the same way as before. Here you see the 8 products explicitly represented, and those 8 products are also shown here. And you can see that P1 has the 7 features that I've mentioned earlier. It's got a price or a cost of 148 euros, megapixels 8, optical zoom 4x, etc., etc. And those are just they're just a bunch of features and a name associated with them. But ultimately, what we want to do is rank the items we get back, and so we want a model that actually connects for us the importance of a particular attribute with something which is important to us. So the model then that a user would have possibly would be to value have measures associated with value and quality, or this could be provided by the system itself. So you can see that here what we've done is for each feature, price, megapixels, etc., for value ranges, we have associated values of quality and economy for those features. So we've done a mapping from the feature space to the quality and economy dimensions, and then I am going to measure the utility of a product multiplying by those measures by the interest in those measures. So we would have for the user an interest in quality and an interest in economy. So the user, if you will, would have a profile that would indicate their interest in quality, and that would be their interest level, and their interest level in terms of economy. And so the utility of the product returned for an individual user would modify the contribution of the product that's returned and its quality and economy figures by the interest level that particular user making the, engaging in this interaction with the system directly. So here we've got two particular users, CU1 and CU2, and one of them has an 80-20% interest in quality and economy, and for user 2 it's a 40-60. So for products P1 through P8, we can compute quality and economy measures for those products. That's easy to do based upon this particular table here. By the way, this information is not included in the model that I've provided, but could easily be done, and it would be an interesting indicator of your understanding of the Prolog model to add it. However, this is not a requirement for this in class. So we can compute the quality and economy measures. So we can compute the measures that would be associated, the utility associated with user 1 and user 2 for all of the products if they were to be satisfied for a particular query. And you can see that there are significant differences between the two users. So now we can actually look at similarity. And similarity here is just weighted as we've done before. So here you've got similarity expresses an item with its with respect to a particular requirement, and so we can weight the responses of the system according to the requirements and the user model, which the presumably is part of their particular profile. But that's just a simple distance similarity. but in reality, the users may actually want to maximize something. They may want to go through a process wherein they say, I want to maximize this first, and then I want to minimize something else, and so on. So it's a structured searching of the space rather than just a ranking from those which are satisfied from the initial set of requirements. So let's talk about how we could go about this process of dealing with case-based recommenders. Because here typically there's, I don't know what I want. But what we want to do is not search the entire space all the time, but search subspaces based upon what the user has said yes or no. So let's just imagine a dialogue. So critiquing is basically the user saying, no, let's just stick now with price below this. So it's rather taking out, if you will, subspaces so that we can make progress. So here's an example where we initially started with everything and we got back a set of things, but now looking at price and megapixels, just to choose 2 dimensions, what we want to say is, okay, I really want to focus on price reduction. So the user now has specified a threshold above which they do not wish you to consider going forward. So we will now consider queries which will always include price less than a certain amount. So we now may well relax constraints in other dimensions, but we will never relax that price constraint. So we will always be searching the non-grey region of the space. Obviously, this could be a multi-dimensional search space. We're just making it simple here so that we can actually make some progress. So I gave you back something, but you didn't like it. That's the implication here. And now you're saying, let's not consider anything with a price above a certain amount, which means that the next query that goes in will actually only search that sub-region, and it will say, oh, okay, the most similar item is the one that's closest to that boundary. And so probably we will relax a constraint that would mean that we are going to recommend it to someone. So the idea is that I keep doing properties in order to return products from subspaces, and then the most similar item to the one which was actually recommended is the item within that subspace which is returned. And that may involve a relaxation of a constraint. It may not, but it may. And that's the point here, is that I'm constantly putting thresholds in place. They can be multidimensional, right? I can specify, as is implied on this slide, price and megapixels at the same time after an initial response. And the thing that I'm most likely to return is that new most similar item which you see highlighted, and that may involve relaxing some other constraint. Okay, so that's the thing that's going on. So this slide basically says, well, I may do this a number of times, but what I may do now is not do the satisfaction based upon simple planes within particular dimensions, but I may have computed association rules that are related to either features, feature values, or I may have computed values for rules that said, well, they've got this other thing already in their shopping basket, which means that I should give them back a response that looks like this set of features. So dynamic critiques are more rule-based, and those rules will have been extracted based upon transactional data, such as you saw with the retail data set from a few classes ago, or they may have been extracted from other types of behavior. But either way, they are rule-based as opposed to simple feature by feature based, which was implied by the previous slides. And this dynamic critiquing is what I've just said. We iterate through a process of trying to satisfy a query based upon a set of requirements. And if you look, the compound critiques are being driven by some rule base that is a priori derived, and then the select critiques is the user interacting with the set of things which have been returned, and we keep doing this until people are happy. And that's really all that's going on here. It's rule driven, and those rules have been extracted from data which are presumably transactional in nature, much like the retail data set that you saw a few classes ago. So in summary, knowledge-based recommender systems can be constraint-based, case-based. These knowledge-based systems may actually be derived from humans. They may be derived from transactional data that's come from users ultimately, or they may have come from scraping resources on the web. In order for the user to get what they want, there may be some kind of interaction, long-running interaction, which you would typically want to store, and those dialogues themselves may be a source of models that you can use machine learning on to refine over time, because obviously we want to get to a purchase decision as quickly as possible, both because users want that and you want that, because of course the less time they take, the more business you can actually do. Preferences aren't always independent of each other. The simple utility model that has provided is an approximation, but it's better than nothing at all. Okay, thank you.